Next up, we're going to cover something known as Faraday's laws, or Faraday's laws of counting electrons, where we're going to learn how to do calculations involving redox reactions. And in doing so, when we're working with these calculations, whatever we're given, we want to think in terms of moles. Moles of substances involved in the reaction, moles of electrons transferred from one substance to another. So we're going to deal a lot with moles. And so let's look at the amount of electricity. So again, electricity essentially is the movement of electrons. So anytime we're dealing with electricity, we're dealing with electrons. We have a couple things here for you to keep in mind. One is known as Faraday's constant, 96,500 coulombs. Coulomb is a unit of charge, so symbol there is capital C. So it is the charge carried by 1 mole of electrons, 96,500 coulombs. This is the same thing as a Faraday. So a Faraday, it says here, is 1 mole of electrons. A Faraday, again, is the charge carried by 1 mole of electrons, which happens to be 96,500 coulombs. So we're not going to really deal with Faradays so much as we will with coulombs of charge. This will be especially important, as we see here in letter C, when we're dealing with current. So current refers to how fast the electrons are flowing, or how fast electricity is flowing. The unit of current is known as an ampere, or just amp for short. The symbol is just a capital A. And an amp is a coulomb per second. And so we're going to use this as a conversion factor. So oftentimes we are given the current that passes through a solution. We're given the time that that current passes through the solution. So if you're given the current and the time, you can use that to find the total charge that moves through the solution. And if we know the total charge, then we can use that to find moles of electrons. And then once we know how many moles of electrons are transferred, then we can use that to answer the question. So let's take a look at some examples of using current and using Faraday's constant to do some calculations. So here's our first question. How many grams of silver metal will be deposited by a current of 1.00 amps flowing for 9,650 seconds? All right, so let's go over what this really means. So you're making silver metal. So again, we're talking about a redox reaction occurring. Process maybe here known as electrolysis, where you take an electric current, you pass it through a solution, and a redox reaction occurs. And so that's what's going on here. So first thing we need to know is, what is the silver metal being produced from? How do we get silver metal? So let's take a look at the possible half reaction for this process. And so silver metal comes from the reduction of silver ions. So let's say you have a solution of silver nitrate and you pass electricity, an electric current through that solution. Well, what could happen is the silver ions could be reduced, and if these silver ions are reduced, you are going to make silver metal. Now, what's important here in this half reaction are these mole ratios. And so this is why writing the balanced half reaction, we don't really need the whole chemical equation for the reaction in this case. We need the balanced half reaction, and that will allow us to do our calculation. All right, so let's set it up. And so what we want to do is, as I mentioned before, anytime you're given the current, we're going to use that as a conversion factor. As we'll see in a little bit, sometimes you're asked to calculate the current. And so just be thinking of what an amp is, and whether we're trying to find amps or whether we're given amps, and we're going to use that in our calculation. So we're given the current, and we're going to use that as a conversion factor. So what we're going to start with here is the time. So we have 9,650 seconds. Be careful, the time that the current passes through a solution is not always given in seconds. Yet, when we look back here, an amp is coulombs per second. So if your time elapsed time is not given in seconds, make sure you convert it to seconds. All right, so we're going to take this and multiply it by our current, except I'm not going to write 1.00 amps. I'm going to write 1.00 coulombs per second. And you don't really need the 1 second, but you can put 1 second there. Now, keep in mind that this one, this is a ratio, so that 1 is not one significant figure. So that's, 1 coulomb per every 1.00000, an infinite number of significant figures in that value. But this value here is important, 1.00, that is 3 sig figs. All right, so we have the total charge that passes through the solution. We need to know how many electrons this is we're dealing with here that are being transferred. And so our next conversion factor, we want to get rid of coulombs, and we want moles of electrons. So here's where we use Faraday's constant. So 96,500 coulombs per 1 mole of electrons. Coulombs cancel. Now we have moles of electrons. So what can we do with the moles of electrons? Well, we can go back to our, which I erased it, sorry about that, our balanced half reaction. Here we have moles of electrons. We're trying to find grams of silver, so we can use that mole ratio. So we have 1 mole of silver metal that is produced for every 1 mole of electrons that are gained in the process. All right, and then we answer the question. We're trying to find grams of silver, so we're going to convert the moles of silver to grams. And we should get the answer. Go ahead and pause the video and type that up and see what you get. So if you pass a current of 1 amp through a solution containing silver ions for 9,650 seconds, you should produce 10.8 grams of silver metal. Now, which electrode will this silver be deposited on? So interestingly, I've described here an electrolytic cell. What an electrolytic cell and galvanic cell have in common is that the process that occurs at the electrodes is the same. So we're talking about the reduction process, reduction of silver ions to silver metal. So which electrode does reduction occur at? Maybe you forgot the specific names of the electrodes. The electrodes are called cathodes and anodes. So at which electrode does reduction occur? That, of course, would be the cathode. So the silver metal would be deposited on the cathode. Now, again, something else to note is that when you have this situation, electrolysis of an aqueous solution, oftentimes the electrodes are inert. Inert meaning they're not reactive. They're not involved in the reaction. And so a lot of times we use either graphite or platinum or palladium electrodes when we're undergoing an electrolysis process such as what's described here. All right, let's take a look at another example. It says a current of 5.00 amps flows through a cell. This is an electrolytic cell. Again, how do I know? Well, we're using an electrical current to make a non-spontaneous redox reaction occur. So moves through a cell for 10.0 minutes. How many grams of silver could be deposited during this time? And write the cathode reaction, cathode half reaction. Well, we kind of already did that in our last example. So same situation here, except we have a different current and a different time. So go ahead, I'll let you do this one since it's the same as the last one. Set this up and see what you get. Pause now, please. All right, so here's our setup. So I started off by converting the minutes to seconds. So 60 seconds per minute. I'm just going to cancel as I go here just to show you. So now we have the time in seconds. We're going to take the time and multiply it by the current, 5 coulombs per second. And then we're going to convert the charge from coulombs, charge in coulombs, to moles of electrons using Faraday's constant. It's always per 1 mole of electrons. And then according to our balanced Here, let's write that again. Balanced half reaction that occurs at the cathode. We have 1 mole of electrons for every 1 mole of silver metal that forms. And then we take that moles of silver and convert to grams. We end up with a total of 3.36 grams of silver deposited on the cathode. All right, next one. What's current? So this time we are not given the current, but we're asked to find the current. What current must be used to plate 1.75 moles of copper on an electrode in 6.24 minutes? All right, well, we've got to clarify something here. The copper that is being produced, what is it being reduced from? Is it being reduced from copper 1 or from copper 2? So for this example, let's just assume that it's copper 2 that is being reduced, so I'll help you out with that part. So again, we start off with our balanced half reaction. So copper 2 ions gain 2 electrons to form copper metal. I think I'm going to let you try this out on your own. So we're looking for current this time. So remember, an amp is a coulomb per second. We have the time. And so we need to find the total charge that flows through the solution in coulombs, and then we'll have everything we need to calculate the currents. Go ahead and give that answer not in coulombs per second as your final units, but rather in amps. Go ahead and pause, set this up, and check back in a second. Alrighty, so here's our setup. I did it all in one shot, but if you want to break it up into steps, find the charge first, and then take that and divide it by the time in seconds as a second step. That's fine. So took the moles of copper, so we're starting here, and I need that to find how many moles of electrons are gained during the reduction process. And then once I know how many moles of electrons are gained, I can use that to find the total charge that passes through the solution using Faraday's constant. Take that divided by the time that the current passes through the solution in seconds, and we get our current, which is pretty high, 902 amps. All right, it's a little different problem, and we have one similar like to this next. So I'll walk you through a little bit, but I think I'm going to have you do this again somewhat on your own. What period of time, let's find that in hours because it's going to be a pretty long time. What period of time was required if a current of 5 amps was passed through a salt solution, a sodium chloride solution, and 1.00 moles of chlorine gas was produced? So again, same situation as before. We have an electrolysis of an aqueous solution, this time sodium chloride. This time though, we are looking for time. We're given the current and we're looking for time. So remember, an amp is a coulomb per second. We know this and we can find that. So we're looking for time. So think about what you would have to do with that equation, how you would rearrange it to find time, and then you can set it up like that. All right, so let me help you a little bit with our half reaction here. So again, in a solution of sodium chloride, we have sodium ions and we have chloride ions. And so what we're talking about here is taking the chloride ions and producing chlorine gas. So what must happen to chloride ions in order to make chlorine? Are the chloride ions oxidized or reduced? Well, we're going from -1 to 0, so that means the chloride is being oxidized. Let's balance our mass here. So again, the ratio that we're looking at is right there. So 2 moles of electrons lost for every 1 mole of chlorine gas that is produced. All right, let's go ahead and pause the video and set this up. Alrighty, here's our setup. So we're going to take the moles of chlorine gas produced and use that to find moles of electrons that were lost. And then once we know the number of moles of electrons that were lost, we can convert that to charge in coulombs using Faraday's constant. And then, like I said before, An amp is a coulomb per second, and so if we're trying to find time, we can just swap those and we get time, or technically seconds here, I guess, is charge over current. Charge in coulombs divided by current in amps will give us time in seconds. So as I said before, it's a pretty long amount of time, 38,600 seconds. The question asks for the time in hours, and so that's how we convert that to hours. So 10.7 hours to produce 1 mole of chlorine using that current. All right, I'm going to let you do this one all the way on your own. Similar to the last one, this time we're looking for the time in minutes. We're given the amount of calcium metal that is deposited, and then we're given the current as well. Go ahead and pause the video and set this up. So hopefully you're seeing a pattern here. First step is to write the balanced half reaction. We're making calcium metal from the reduction of calcium ions. So again, important ratio here, 2 moles of electrons gained for every 1 mole of calcium metal that forms. We're starting with grams this time, so we're going to convert that to moles of calcium, then moles of electrons to charge in coulombs. Take the charge divided by the current, and we'll get the time in seconds, which we will then convert to minutes, 7.65 minutes. All right, so that concludes this lesson, and that actually concludes this unit. Thanks for watching.